stats, statistical analysis tools that you can use in experiments. All right, I'm going to probably add this on. I'm obviously doing it for the first time here for you guys, but I'm doing it for a couple of reasons. One, with the STEM program, a lot of the students are going to have to do research and be able to do statistical analysis of that. It's almost impossible nowadays to do any kind of data collection without doing at least a standard deviation. Now, I always in Chem 1 just had you guys, when we had books, we had charts like this for density. Remember Popcorn Lab? Remember? We had at least 4 times we saw these kind of charts up there. The acid-base, like the Tums Rolage one, remember that? All of those had charts like this, but the difference was all we calculated were the means and then the average deviation. And as I'm going to show you when I pass out these papers, that's not very useful. The average deviation, as you'll find out, doesn't tell you a whole heck of a lot. All right? And neither does the mean, the difference in the mean. So you might look at this data and say to yourself, oh, well, clearly juice 2 is better than juice 1. But you don't know that. As a matter of fact, we have very similar data. I guess I should be down here. We have very similar data for period 1 this morning. And they had 5 data blanks. And their means were very much like this. They're probably different by about 3 milliliters. They probably differ by about that much. And you might say to yourself, well, geez, that's like 30%. I mean, bigger. Or you might think to yourself, if you're not thinking statistically, so there's clearly this juice is better than that juice. But it didn't turn out that way. And I'm going to show you tomorrow when we do a t-test, and I'm going to probably have their data up there as well. I want to show you the difference between your data and their data. They had such a spread. For example, they had a number like 6.75 and another number like 16.41. Because they had such a spread in there, and even though they averaged out to be about the same as yours, when you run a test on it, it turned out that that difference, that 3 milliliters of difference, was not significant. And it would not prove that juice 2 is better than juice 1. All right? So you have to take this into account, the deviation. Now, I'm going to teach you today how to calculate deviation. I don't think I can leave this up here. I'd like to be able to come back to it. But we are going to use your data, which will be nice because you only have 3 points, so that's a little bit shorter than theirs was. I'm going to use your data to calculate standard deviation in a little bit when you're working on the worksheet. But let's talk about what standard deviation is first. What did we do to get the regular deviation? Because it's part of. Getting the regular deviation, you simply took the mean minus this one, and you took the absolute value of it, right? Okay. Well, that's what you're basically going to do again. That's one of the steps of taking a standard deviation. All right, but there's a lot more to it, and you're going to see what that more to it is in a minute. All right. Okay. I'm going to give you the sheets so you don't have to take notes on this because I actually have them for you. Okay. So here's the first one. And it has dogs on it. Yay! My dog is there. He's on the far right. He's a Boston Terrier. Well, he's kind of like a Boston Terrier. He's small. He's a mix. See the one on the right, Buddy? There's Buddy. Wait, I'm going to show it to the people at home. There's Buddy right over there. There's Buddy. I'll listen to Buddy there. Right there. All right. Okay. I don't know why. Now. We're going to, so you don't have to write this down, but I want to kind of explain it to you, okay? So watch as I explain this. Yeah, you watch up here, look up here. Basically, a standard deviation using a population, where the population is everybody, everybody you want to know. A good example of a population standard deviation would be like if I wanted to find out the standard deviation for a test, the test you guys just took. I know all the values, because I have all your scores on that test. And I'm not trying to extrapolate that to some other area. I just want to see how your class did. It's different than the juices I was doing before. That's not the same thing. I was trying to see, well, which juice is better? So I'm just taking a sampling of these juices, and I'm going to see which one's actually has more vitamin C in it. All right. So I do want to extrapolate that to a larger sample set. I can't test every juice. Okay. So in the case of whether to use a population, or you're going to see in the next page a sample deviation. It all depends on whether you have all the information. If you have all of the data points that you care about, you're not trying to apply it to some larger sample size, or to some larger group, then you could use the population one. And basically, you're going to measure how spread out the numbers are. Well, a regular deviation does that too, but a standard deviation does it, a different way, and it's actually more accurate. what you do is you get the square root of the variance. Now that sounds fancy and scary, but it really isn't. The variance is a little complicated to do. It's actually not as much complicated as it is tedious to do, which is why I'm going to probably look for next year when I bring this into Chem 1, I'm probably going to look for a program that after I show you how to do it once, you could use your graphing calculators to be able to do it. I'm sure there is one, where you just plug the numbers in and it gives you the variance and it gives you the standard deviation. All right, so here's what you have to do. That's the equation right there. And again, it looks scary, but don't let it scare you. Oh, and by the way, you will find throughout the papers I'm going to give you, I normally don't use S. It just happened to be a good one I found. It blew up well, and you can see everything on your paper. But generally, the formula for standard deviation is a sigma. It looks like this. It's a sigma, like it's a Greek letter. All right. Anyway, the standard deviation equals the sum of. Now, x, what is x and x with a line over it and n? What do all those things mean? Well, they're all written down under here what they mean, but let me explain. X is just the value, individual value at the data point. X with a line over it, you should know from math class. What does that mean? What does that mean? Yeah, it means the mean. It means the average. N is the number of data points you have in the set. So in the case of your lab, how many do you have? 3. Okay? So basically, it's the sum of these guys, the difference between these guys, squared, divided by how many you have, and then you take the square root of it. The variance is actually everything but the square root part. So everything underneath here is a variance. The square root of the variance is the standard deviation. That sounds scary, but it really isn't. I'm going to show you with some examples of using dogs in a minute. But before I do that, I want to show you what would look like if I do have a random sampling, a normal curve looks like. Standard deviations can be plotted on this curve. And let me show you why they're useful. Y'all watching? Emily, I need you to pay attention. All right? Why they're useful. If you look on here, this is one standard deviation on this curve. And one standard deviation above or below the mean. Notice it's called a normal curve. And one way you can remember that is, basically, if you fall in that one standard deviation, you're normal. I mean, it's used in a lot of areas. This kind of stuff, this kind of analysis is used in, medicine, population statistics, polls, taking, polls of people for, even for, politics and stuff like that, or opinion polls. Basically, 68% of your data, whatever it is, whether I'm doing an experiment, if I do a standard deviation, it's assuming a randomly distributed, normal curve. 68% of that data will fall within one standard deviation either way. So I'm pretty confident about that. 2 standard deviations, look at that. That's 95% will fall within 2 standard deviations either way. Okay? So you basically only have 5% on either side. That's going to be some really crazy stuff. The chances of that happening are very slim. Think of height. If I took the entire building, entire school, I wanted to find out the population, it would probably fit a curve just like this, where your mean height would be somewhere around, for guys, maybe around 5'11", for girls, maybe around 5, I don't even know. But the point is, there are some people who are really, really short, you see them walking around, and you are some people who are really, really tall. But if you were to do the stats, you would probably find that 95% fall within 2 standard deviations of that mean height, of whatever the mean height of people, of kids in Berwick are. Okay? All right. So that's what it would look like if you graphed it. And, of course, this is where, when it comes to labs, when it comes to experiments, we need to use a standard deviation to tell how confident we are in that data. In general, if I'm talking something falls within 2 standard deviations, 95% of the stuff's going to fall in there. Yeah, I'm pretty confident about that. So if I say my answer is 3.7 plus or minus, 2 standard deviations, whatever it is, I have a pretty good idea of that. That's pretty good. It's going to fall in that area. The real answer should fall in that area, 95% of the time it will. All right. Now let's look at how we calculate it. And using dogs, so you have all of this on your paper as an example. If we take the height of the dogs, okay, all right, measure all those heights and get the mean. And the mean is 394, I think it's millimeters or centimeters? I forget. Millimeters? Okay. So 394 millimeters high is the average height of dogs. Because I simply, what did I do? I added up 1, 2, 3, 4, 5 dogs. I divided by the 5, added all their heights, and I got 394. That calculation is written there for you. You can see it there. See it? Okay, I don't have all of your papers not on here. Okay, only a few pictures here. So basically, here's what you're doing next. You're going to subtract, like you did in those charts for the popcorn lab and the density lab and the juice lab you're going to do in a few minutes. You subtract the mean and each of those values. Now notice you'll get negative values and you'll get positive values. Some guys are below the mean, obviously. Some guys are above. You don't have to worry about taking an absolute value of them, as you'll see in a little bit. What's one reason I don't have to worry about taking an absolute value, considering that's the next calculation? Because I'm going to, no, not because it's a square root. Wrong. Why? Because I'm squaring them. When I square a negative value, it becomes positive, you see? So I don't have to worry about taking the absolute value of them. I could have negative value. They're on the other side now of your paper. You turn them over. So look what you did here. Y'all, let's go back for a second. I took all these deviations, 206, 76, minus 224. Okay, I took all those deviations, 206, 76, negative 224. I square each of them, I add them all up, and I divide by 5. Why 5? That's how many there are. That's the n. That's what n is. And what I'll get is the variance 21,704. What does that mean? Well, right now it doesn't mean anything. All right, we're going to do something. It does mean something, obviously. It's a measure of the variability. The higher that number is, the more variable your data is, the more variation there is in there. As a matter of fact, before I even go on any further and show you the rest of this calculation, I want you to realize what would make that variability higher. We don't want a lot of variability in an experiment, do we? We want experiments that, boy, it'd be nice if everybody's got the exact same data point, and we don't have somebody yelling out 40 when everybody else is 12, right? And she's going to tell us to die soon. But you know what I'm saying? Like, that was clearly an outlier. You knew that that was wrong. I knew as I'm writing them down. I didn't even write the number down. Not because I'm brilliant, but because we have an intuitive sense of numbers that when I'm writing 12, 11, 11, 40, something's wrong there. But I want you to realize it's not always going to be that easy. So, if it's not going to be that easy, let's just look at what are the things that make variability greater. What is it? What do you think?
A bigger difference in like height, like you have really tall dogs.
Right, so these numbers being larger would make a larger variance, right? Agreed? What else would help make this, what will make this number smaller? What can I do to this? More samples, right? The more samples, why do you think experimenters who are doing research don't just do 2 or 3 trials and say, here's my results, I'm done. I think this juice is better than that juice, or I think this stuff causes cancer. You can't do that with 1 or 2 trials. You have to do it over and over and over again. Why? Because it reduces your variability. The larger this number is, the smaller the overall variability is going to be, correct? So you can basically, you're more confident in your results if you do, the more trials you do. You see that? It's mathematical. It's not just common sense. It's also mathematical. So to get the standard deviation, which again is sigma, I would get the square root of 21,704, and I get 147.32. So I'm pretty confident that 68% of my value is going to fall in from the mean plus or minus 147.32, right? I'm pretty confident about that. If I really want to be confident, take 2 standard deviations, 95% of the value is going to fall in there, right? I could do that. But one of them, 1 standard deviation, that's what you would get, okay? Why square the differences? Why not just, this is on the page I'm about to pass out to you. This is the last page, you're going to do some work. I have other stuff to do after this. But why square them? That's what I want to I want you to skip a little bit down to the bottom of this page, and I'll show you what I mean. Why not just take, well, if you look at this, now I'm on this page here, and I'm going to talk about this sample thing in a second. But skip down to where it says y squared the differences, the part right around here. Okay? Y'all looking at that? Well, let's take a look. The first thing it says, well, if we just added up the differences and you didn't even, do the sum, if you kept all the signs, what would you always get for a deviation? Or for the average deviation, what would you always get? 0. Because you're going to have the same number above and below the mean. So you're always going to get 0. So what did we do in Chem 1? Back then, I told you to take the absolute value of that. And that makes sense, and that works. But here's the problem. Take a look at these two values. These are the ones up here. Now you can look up here. Okay? These guys are clearly not the same, right? There's a lot more variability here, isn't there, than there is here. Would you be more confident with that data than you would with this data? This is all over the place. Kind of like, and you're going to see this tomorrow, kind of like period 1s look like. Their juices, it was, I said, 16, 6, 8, 10, 12. It came out to be about the same average as yours, but way all over the place, kind of like this. If you do the deviations the old-fashioned way, the way we did in Chem 1, you'll get exactly the same numbers. Both of these guys have exactly the same average deviation. But look what happens down at the very bottom if you square them first. If you square them in this part down here, you don't get the same average deviation. The standard deviation is higher for this one, which is exactly what you'd expect. You see what I'm saying? That makes sense? Mm-hmm. All right. Now, the only other thing I need to mention to you before I let you start on the problems is the difference between, and it's a very small difference, between population, standard deviations, and sample. This is the top of that page. Okay? Look at that formula. It's the same formula, with the one exception. What's that? Subtracting. Yeah, you're subtracting 1 from this. Now, this is called degrees of freedom. The end down here is how many degrees of freedom you have. And you're actually taking away 1 degree of freedom. Because, here's, the best way I can think of to explain this is this way. The degrees of freedom are basically how many chances you have for variability. Okay? And you're going to take away 1 of them because when you do, normally you would have 5 groups, you have five measurements, you have 5 chances. But you're not so sure about one thing about this guy. You know what it is? The mean. Because you're doing a sample of a larger group, that mean you're getting itself isn't certain. If I'm doing the tests, everybody's tests in this room, I know the mean. I know the mean exactly what the mean is. Right? I just add them up and divide by 11. All right? However many people in the class. But if I'm saying I want to extrapolate this to the general population of people, I don't have every person in the world, so I don't know what the mean value is, and so I'm actually going to subtract away 1 degree freedom, which makes the denominator slightly smaller. Right? What's that going to do to your overall problem? It's going to make it worse, right? It's going to make more. So you're not overestimating your confidence when you're only doing a sample. You're basically saying, well, I'm going to underestimate my confidence level here because I'm not sure even about the mean. All right, so I'm underestimating my confidence level here. Now, and of course, still, if n's larger, you're still going to be good, right? If n's a very large number, 150, I do 150 tries of the same thing over and over again. Subtract 1 from 150 is not that big of a deal, you know. But if you have a very small sample size, you know, you got problems, right? That's why you always try to get large sample sizes for chemistry and for any science. All right, now you're going to do problems number 1, problem 1 first, and problem 7, which is your juice lab. Here's the question. Read problem 1 there. I'm telling you in problem 1, I just care about that data, those snowfalls, right?
Where is there?
Oh, I didn't give it to you. That's right. That's right. I'm sorry. Here you go. There you go. It's on the worksheet coming around. Okay. And look at problem 1. All I care about there is that particular set of data. So I want you to use, you all look at here, you would just have n underneath here. You'd be using what's called the population standard deviation. However, on the backside, problem 7, you'll be using this formula with the n minus 1 because you're trying to, compare that to the, generic idea of all the juices that you're testing. And you can't test every juice. Okay? All right. Do that right now. I'll pause the camera and we'll do the next part later.